Hello students, welcome to Science Pathashala. This is Girish Babu. So in this class we are going to discuss about numericals on nuclei. This nuclei chapter is very important. In this nuclei there are concepts like mass defect, binding energy and specific binding energy. They'll ask based on these formulas, they'll ask the questions. Find out the binding energy, find out the mass defect, find out the specific binding energy. Okay, so please do watch video till end. Definitely you will get benefit from this video. Okay, so let's start the class. See, before going to the class, we are going to discuss some numericals and equations. What are the equations we are going to use in this video, right? So we'll discuss some concepts, then we'll move on to the numericals. See, first thing is mass defect. See, what do you mean by mass defect? See, there is a name itself, defect. Defect means there is a defect in mass. So the mass defect is the difference between atomic mass and some of the constituents of masses. That we are called as what? Mass defect. So how it is mass defect we are going to understand. What it is exactly. So I'll take one example here. I'll take carbon. So atomic number 6, mass number is 12. So how many protons? Protons is equal to 6, neutrons is equal to 6, right? See, if I tell you there are 6 protons and 6 neutrons, they all are independent now. See, 6 neutrons independent and 6 protons are independent. Okay, I put them in weighing machine. See, there is weighing machine here, 6 protons here, 6 neutrons here. So this is also weighing machine. See, protons, neutrons, we are together called nucleons. So here, this is protons and neutrons separately, that we are called as what? Nucleons. Okay. So see, what is the weight of this nucleons? That is protons, neutrons, and note down the reading. Then coming to this, I'll bring protons, neutrons together. Now I'll bring this protons, neutrons together, and right now they are all part of which nuclei? Carbon nucleus. Now if I'll bring protons and neutrons together, combined together, we'll get nucleus, right? Which nucleus it is? Carbon nucleus. And also I'm going to weigh this weight of nucleus. So that I'll put it on weighing machine. Now which one will be heavier? See, there is a protons and neutrons. Here there is a protons, neutrons together become a nucleus. So whether nucleus will give you more weight, or else this nucleons will be the more heavier. So if you check this, definitely nucleons will be the heavier compared to the nucleus. See, there is a mass, there is a difference, mass difference. See, there is a mass difference between nucleons and nucleus, that we are called as mass defect. Okay, clear? Got it? Yes. Now see here, the mass of nucleus is always smaller than sum of the masses of nucleons, that is protons and neutrons. See, always whatever you will weigh, that individual weight, protons and neutrons, always will weigh, they are heavier than nucleus. Clear? So what the difference, that mass difference between nucleus and nucleons, that we are called as what? Mass defect. See, there is a formula, important formula for this mass defect, that is ZMP. That is, I'll write it here again. Z delta M is equal to Z mass of proton plus A minus Z mass of neutron minus M. Okay, clear? See here, what is Z here? Atomic number. Z is atomic number. What is A? Mass number. See, what is mass number? A is equal to, we know that formula, Z plus N. Then what is N is equal to? A minus Z. This A minus Z, this is that. That is A minus Z is equal to this. This is nothing but a neutron, right? So then mass of neutrons is equal to total mass of atom, M. Clear? Got it? Yes, this we have to remember this formula. This is very useful for your exams. Okay, so next see here, coming to this is all about mass defect. See now this nucleons means protons, neutrons are together called nucleons, and nucleons to form a nucleus, right? So now how much energy required to break this nucleus? That energy we are called as binding energy. That's it. Okay, see, we are going to break this nucleus into nucleons. How much energy we required for this to break this nucleus? That energy we are called as what? That is binding energy. See here, this is nucleus. We are going to apply some energy on this nucleus. This nucleus is going to split into protons and neutrons. That we are called as nucleons. That we are called as what? Nuclear binding energy. Okay, clear? Or one more definition, how much energy required to bind these nucleons into nucleus? That is also called as binding energy, vice versa. So how much energy required to break this nucleus? How much energy required to bind these nucleons? That we are called as what? Binding energy. Okay, see, nuclear binding energy is the energy required to break up nucleus into its components of protons and neutrons. That we are called as what? Binding energy. Clear? Got it? Yes, see, there is a formula for this binding energy, that is Be is equal to delta M 931.4 MeV. This is the standard formula. See this, how do you get this formula? Means that is E is equal to mc square, famous formula, that Einstein's mass energy equation. E is equal to mc square. If you do some calculation, if you substitute this C value and everything, if you do the calculation, you will get this thing. Which one? That is binding energy is equal to delta M into 931.4 MeV. Clear? See, we have to remember this formula. This is important, but while solving the numerical, this formula is very important. Okay, you have to remember this formula and this formula. And finally, we'll come to know this specific binding energy or binding energy per nucleon. So this also we are called as specific binding energy or binding energy per nucleon, that is B dash, or there is one more name for that, EBN. EBN is equal to BE by A. Binding energy per nucleon. Binding energy per nucleon. The binding energy we can also write it as EB is equal to delta M into 931.4 MeV. Okay, so this binding energy per nucleon is equal to binding energy by atomic mass number. Clear? Got it? Yes, these are the formulas we have to remember while solving the numericals. We'll going to apply all these formulas in the equations. Okay, let's start the class. See, first numerical is like this. Calculate the mass defect. Calculate the mass defect, binding energy and binding energy per nucleon of an alpha particle in MeV, mega electron volt, from the following data. So mass of alpha particle, this is alpha, mass of alpha particle nucleus is 4.001260 U. Mass of neutron is 1.00866 U. Mass of proton is 1.00727 U. Okay, atomic mass unit, it is in terms of atomic mass unit. Okay, so first write down the given data, what they given. See, what we have to calculate, mass defect we have to calculate, binding energy we have to calculate, specific binding energy or binding energy per nucleon we have to calculate. See what they given, mass of proton they given, mass of proton how much, 1.00727 AMU or U, AMU. Okay, next mass of neutron is equal to 1.00866 U. Then so mass of alpha particle, mass of alpha particle of nucleus how much, 4.00126 AMU or U, whatever it. Okay, So next, what we have to calculate? We have to calculate delta M, mass defect we have to calculate, EB we have to calculate, binding energy, and EBN, that is specific binding energy, we have to calculate. So just now we have discussed that what is formula for this mass defect delta M is equal to ZMP plus A minus Z Mn minus M. Okay, so now substitute the values. Delta M is equal to, what is Z? Atomic number of alpha is nothing but a helium. See, alpha particle is nothing but a helium. Helium atomic number 2, mass number will be 4. Okay, so atomic number how much? 2 into, so MP how much? Mass of proton 1.00727 plus, so atomic mass number how much? 4. Atomic number how much? 2 into Mn how much? 1.00866 minus mass of alpha particle nucleus how much? 4.00126. Okay, so if you do this, you will get 2.2 into 1.00727 is equal to 2.01454 plus 4 minus 2, 2. 2 into 1.00866 minus 4.00126. So if you do this, this is as it is 0.01454 plus 2 into 1.0086 how much? That is 2.01732 minus 4.00126. See, if you do this addition of 2.000154 plus 2.01732 is equal to 4.03186 minus 4.00126. If you do this, you will get around 0.03059 U. This is the value for this mass defect. Okay, now next what we have to calculate, mass defect is done. How much? That is 0.030595 U. Then what we have to calculate? We have to calculate binding energy. Binding energy, that is EB is equal to, so what is the formula? This mass defect into 931.4 or 0.5. Okay, so if you substitute this, that is binding energy is mass defect how much? 0.030595 into 931.5 is equal to, so you will get around 28.55 MeV. See dear students, please do your calculation. I might be wrong because you have to do the calculations. If you take the more digits, you will get different, some little bit changes in that answer. Just check out near to 28, then it is correct only. Okay, so next, this binding energy finished. Then what we have to left out with? Specific binding energy, that is EBN is equal to, so binding energy per nucleon, that is A. So EB how much? 28.55 MeV divided by mass number how much? Atomic mass number, that is 4. If we do this, you will get 7.1375, that is MeV. This is the specific binding energy. Okay, see this question they'll ask in twice, 2020-23 March paper and 2020 July paper. See, in this what we have to what we did here, we calculated that mass defect, binding energy, and specific binding energy. Simple, right? So you know the formula, you know the values, you know the mass number and atomic number, then easy to find out the answer. Clear? Just note down the calculations. We'll move on to the next one. See, next one will be like this. Calculate the binding energy and binding energy per nucleon of an oxygen nucleus from following data. See what they given. Mass of proton they given. How much? 1.0078 1.007825 U. Mass of neutron 1.008665 U, and mass of oxygen nucleus is 15.995 U. Okay, see oxygen, we know that oxygen atomic number is 6, atomic number is 8, mass number is 16. Okay, so now we have to calculate this binding energy. See, they'll ask only binding energy. If we want to calculate this binding energy, we should calculate this mass defect, that is delta M. Delta M is equal to formula Z MP plus A minus Z Mn minus M. Okay, so Z how much? Atomic number how much? 8 into MP how much? Mass of proton 1.007825 plus mass number how much? 16 minus 8. Mn how much? That is 1.008665. Okay na? Next minus 15.995. so if you do this, you will get around 8.0626 plus, so 16 minus 8 only. 8 into 1.008666 is 8.0692 minus 15.995. Okay, so if you do this, you will get something 16.1319 minus 15.995. so then delta M is equal to 0.1369 U. This is the mass defect value. Then what we have to calculate? We have to calculate binding energy as well as specific binding energy. Binding energy formula Bn is equal to mass defect into 931.5, or you can neglect this 0.5 also. Okay, so delta M how much? 0.1369 into 931 is equal to 127.45 eV, mega electron volt, specific binding energy. Okay, so next, this is binding energy. EB is nothing but a binding energy. Now we will discuss the specific binding energy. Specific binding energy we are indicated by EBN. EBN is equal to EB by A. EB means binding energy. So A means atomic mass number. Binding energy how much? You got 127.45 divided by 16. So you will get this 7.965 mega electron volt, or it is near to 8 mega electron volt. So if you take this 9.931.5, you will get some different answer, 8 point something you will get. Okay, that's fine. Near value they will consider. Okay, so simple, right? Yes, they'll ask this question in 2007. They asked in 2017 July board exam. Okay, clear? Yes. See, next one will be like this. Calculate the mass defect and specific binding energy of nitrogen given that rest mass of nucleus is 14.0034, mass of neutron 1.00867, mass of proton 1.00729. What we have to calculate? We have to calculate mass defect we have to calculate specific binding energy. Before that, see, if the last two, we have to calculate binding energy also. Without binding energy, we cannot do this specific binding energy. Okay na? So delta M is equal to, what is formula? Delta M is equal to Z MP plus A minus Z Mn minus M. So Z how much? It is nitrogen, means nitrogen atomic number is 7, mass number is 14. So Z how much? 7. MP how much here? MP 0.00729, right? S into 1.00729 plus, so A minus Z, 14 minus 7, 14 because atomic mass number, A is 14, 14 minus 7, 7 into Mn how much? 1.00867 minus M how much they given? 14.0034. 14.0034 they given. 34, yes, 34. Now if you do this, you will get 7.05103 plus 7.06069 minus 14.0034. Now, so if you do this, you will get 14.11172 minus 14.0034. So delta M is equal to 0.10802 U. Okay, now this is the mass defect. Now what we have to calculate? We have to calculate binding energy. See, they ask only two things: mass defect and specific binding energy. To calculate specific binding energy, we require that binding energy, that is EB is equal to, what is the formula? Delta M into 931. Delta M how much? 0.10802 into 931. You will get 100.56 MeV. You will get. Once if you calculate this binding energy, what we have to calculate? We have to calculate specific binding energy, EBN. Specific binding energy is equal to EB by A. What is EB? 100.56 divided by how much A? 14. Okay, then EBN is equal to how much? If you do this, you will get around 7.22988 MeV. Okay, clear? Or you will get something 7.1 something you will get. Please do your calculation, take calculator and do the calculation part, then you will come to know how to do these calculations. Okay, so I might be wrong, please do your calculations. You will get around 7 point something, 1 or 2 or 7.18 something. Okay, yes. So next question will be like this: find the binding energy per nucleus of the carbon nuclei and oxygen nuclei having rest mass 12.001 U and 16.00744, okay, respectively. Given mass of proton they given, mass of neutron they given. So what we have to calculate? We have to calculate the binding energy per nucleon, that is specific binding energy we have to calculate for carbon as well as oxygen. So if you want to calculate this specific binding energy or binding energy of carbon and oxygen, we should calculate first mass defect. Okay, so what is the formula for this mass defect? That is delta M is equal to Z MP plus A minus Z Mn into m. Okay, so first we have to calculate carbon. Case 1, I'll take it as carbon. Carbon atomic number 6, mass number 12. Okay, so here delta m is equal to, what is the atomic number of carbon? 6. mp, how much they given? 1.007274 plus a minus z means 12 minus 6 into how much? mn 1 point c. This is 1 point. There is a point miss agide. So 1.00866 minus m how much? That is 12 they given. 12.0001 they given. Okay. So now if you do this, you will get something 6.04362 plus this, you will get 6.05196 minus 12. If you do this, you will get something 12.09556 minus this zeros you can neglect, or if you want to do it, 12.001. If you do this, you will get delta m is equal to 0.09556 u. Okay, so once if you calculate this, what we have to do, we have to calculate the binding energy. Binding energy EB is equal to delta m into 931. So delta m how much? 0.09556 into 1931 is equal to 0.09556 is how much you will get. Do this calculation again. I am writing this. So do this calculation. So you will get 88.9636 MeV. Okay. So if you calculate the specific binding energy, EBN is equal to EB divided by A. That is EB how much? 88.96636 divided by A means 12. So you will get 7.413 mega electron volt. This is the specific binding energy of carbon. This is the binding energy of carbon. This is case 1. Now same thing for oxygen. Already we have discussed one type of numericals on this oxygen. Fine. See, same method. Please pause the video, do yourself and cross verify whether you are whether what we are doing whether correct right or not. Okay. So 8 and 16. Atomic number is 8. Mass number is 16. I'll substitute directly into the formula. That is delta m is equal to Z how much? Z 8 into MP how much? 1.007274 plus 8 minus 6, 8 into 1.00866 minus this is going to be changed, that is 16.0074. Okay. So if you do this, you will get something 8.0581 plus 8.06926 minus 16.0074. Okay. So now if you do this calculation, you will get around 0.12 U. Once if you done this calculation, what you have to do? You have to do the you have to find out the binding energy. EB is equal to delta M into 931. So delta M how much? Delta M how much? 0.12 into 931 is equal to 111.72 MeV. Okay. Next, what is specific binding energy? EBN is equal to EB by A. So how much EB? 111.72 divided by A how much? 16. If you do this, you will get 6.9285 mega electron volt EBN, or it is nearly equal to 7 mega electron volt. Okay, this is how to solve the numericals. Clear? Got it? Yes. We'll move on to the next one. See, this is very important thing. They lost this exam in 2017, I think. So, what is this formula numerical? Read out the question first. A copper coin has a mass of 63 grams. A copper coin has a mass of 63 grams. Calculate the nuclear energy that would be required to separate all the neutrons, and means binding energy we have to calculate neutrons and protons from each other. The coin is entirely made up of copper, that is copper atomic number how much? 29, mass number is 63. Okay, so what they given, mass of copper atoms is 62.92960 U they given, mass of proton 1.00727 they given, mass of neutron 1.00866 U they given, Avogadro number they given 6.022 into 10 raised to 23 they given. Okay, so what we have to do, see, this is Avogadro number, everything they'll given. This is related to some mole concept, some chemistry related question this is. Okay, so we have to very careful with this numerical. So we have to calculate delta M first, because energy, nuclear energy that would be required to separate means binding energy we have to calculate. To find the binding energy, we should know the value of that mass defect. Okay, delta M is equal to how much? What is the formula? Z MP plus A minus Z Mn into minus M. What is Z here? 29. Z is 29 into MP 1.00727 plus, see here, 63 minus 29, how much you will get? Something 34. 34 into Mn how much? That is 1.00866 into capital M how much? That is 62. This is 62.92960. Okay, so if you multiply this and this, you will get something. If you do multiplication, you will get answer, and if you do this, and I'm doing directly, I'm applying that values here, 63.50527. You do the calculation part because it becomes lengthy. 62.92966. Okay, if I do all the calculations here, it will take more time. We don't have that much time, because that's why I'm writing directly values, direct values. Okay, so if you do this, you will get 0.5767 U. Okay, clear? Yes. So this is delta M. Then what we have to calculate? We have to calculate EB. Binding energy. EB is equal to how much? Delta M into 931.5. So 0.5767 into 931.5. So you will get something 536.1807. This is for per atom. Per atom. What is the binding energy of per atom is 536.1807. Then what we have to calculate? We have to calculate total binding energy. What is total binding energy? Total binding energy. See, total binding energy, that is EB total, is equal to, so what you will get, this EB into how many, we have to multiply with Avogadro number. See, mole concept will come here, that we no need to concentrate that much. So whatever they'll give this Avogadro number, just multiply to this binding energy. So into 6.022 into 10 raised to 23. Okay, so EB how much? 536.180 into 6.022 into 10 raised to 23. So if you do, you will get 3228.88 into 10 raised to 23 MeV. Okay, this is the total binding energy. Okay, so this is the total binding energy. Clear? This is the answer. This is the final answer. This is how to calculate these type of numericals. Clear? Got it? Yes. Yes, this is all about today's class, students. Already we have discussed numericals on wave optics. If you not means, just go through the playlist, you will get the video. Hope you all like this video. Please click on the like button, share among with your friends, and thank you. We'll definitely continue in the next class with a new chapter with a new another numericals. Okay, thank you.